Hi everyone, my name is Topaz, and today we will explore a topic that is really relevant in applied research, and that's the interrelations between our target labels in the actual real world. And this question will take us on a path from classical categorical classification all the way to regression. So today we will see how acknowledging the interrelations of our target labels can boost the knowledge in our training phase, a better model of the world, and improve robustness. So what's on our agenda? We will start with categorical classification and some hidden assumptions that you need to revisit in order to understand if this approach really serves your learning task best. We will then overview different approaches to utilize your discrete categorical labels. And in this talk, my focus is on deep learning neural network-based methods, but many of them are adaptable to other machine learning techniques. But since this is a short talk, I will just give a brief overview and highlight the main concepts. In the third part, our discrete categories will meet the continuous world, and we will discuss how to leverage them. And lastly, I will give a short cookbook of tips and a decision diagram for you to follow when considering a new task of what seems to be at first glance as categorical classification. So let's start. Considering a task in which we are given an image and are being asked, it is a lion, an elephant, or a giraffe. When looking at it, we do not find ourselves considering the relations between them in order to make that decision. Is that giraffe closer to be an elephant or a lion? This question is irrelevant in this case because since those categories are independent in the context of the input data that we are provided with. So this is a straightforward nominal categorical classification problem. But if we stop to think about it, we realize that many of the categorization tasks around us actually have a relation between the target categories. They have an order. So if it's product rating and recommendation, how likely is an offer to be the best fit for a specific user? If it's age prediction in order to adapt user content and offerings, or medical diagnosis. So especially in such cases, some mistakes have dire consequences compared to others. So misclassifying severe medical stage with a good health stage obviously does not have the same consequences as misclassifying severe diagnosis with very severe stage. So we want our learning to be cost sensitive because some misclassifications have greater risks than others. Let's start with the basics and understand its limitation, nominal or classical categorical classification. Be alarmed, this part of the talk has formulas, but so bear with me, and the following chapters after this one will be almost equations free. So from now on, let's assume we are given measurements, the X measurements, and are being asked, sorry, to predict the weather for the next day. Will it be cloudy, sunny and hot, or stormy weather? So we have discrete targets, cloudy, sunny, rainy, and we output prediction, the prediction that tries to describe the probability of each option given an input measurement X. So if we use softmax as our last activation layer, we will get prediction where each entry is between 0 to 1 and the entire vector sums into 1. So basically by doing that, we assume that our categories are mutually exclusive. And assume that in the training process, we have specific sample where when the measurements were taken, it was indeed sunny for the next day. So the true label for this specific measurement X is sunny. So I highlighted here that one in yellow. And we predicted this output vector. We predicted 64% of it being sunny when it actually was sunny. So how do we encode the true category for a training process? Well, the most common way is to use one-hot vectors, where only the entry of the true class is labeled as 1 and the rest are zeros. So when the training process will converge, it will try to mimic that one-hot encoding. And what it will do is basically have just one dominant class, the one that's labeled here at 1, and all the rest will be pushed to 0. So it's like pushing all the other classes infinitely away from the true class. And this may be desirable when the classes are independent. However, it may also lead to overconfidence. But given that prediction, how do we measure how well are we? Because we actually asked the network to learn that this should be a 100% prediction, not only 64. So the most common categorical loss is the cross entropy loss, which I'm sure many of you probably used many times. Now let's take a deeper look. When we use one-hot labels, where only the entry of the true class is set to 1 and the rest are zeros, we can see that the contribution of a specific sample to the cross entropy loss only takes into account the true label, the true class, because all other entries are 0. So we'll only have penalty for the 64 compared to 100% right here. It doesn't care that we predicted 28% cloudy, 8% rainy, only that this 64 is still far from 100. So basically what it does, it balances the true positives over false negatives of this true class. And that's it. And one more thing, it penalizes false negative of the same class, of different classes the same way. So if we have false negative rain prediction, meaning that we missed the rain prediction, it will have same penalty as missing a true cloudy prediction. But some misdetections have higher risk than others. So let's say the implications of missing a rainy day are more costly than missing a cloudy day prediction. So let's consider here that this is one alternative for prediction and this is the other. So basically for the true class, both of them have 64% prediction of the true class, but I switched here the order between the alternatives. So before it was 8% rain, but now it's 28% rain. Will one alternative have a different effect on our loss compared to the other? Well, basically, using the cross entropy with one-hot vectors, then no, only the middle one right here will have an influence. So basically, we know that some misclassifications are worse than others. So it's not only the type of class we missed to detect that we care about, it's what we mistaken it for that we should care about as well. So we want our learning to be cost sensitive. So mainly we want to A, penalize misdetections, false negatives differently for each class. B, we also want to penalize false positives, not only the balance of true positives and false negatives. And C, there are cases where some false positives should have greater risks than others. So those two papers suggest adjustment for the cross entropy loss in order to address it. One is the bilinear cross entropy, and the second one is the real world cross entropy. So the first term right here, you are familiar with that one. It's the class-weighted cross entropy, especially popular in unbalanced classification problems. Each type of false negative gets its own class weight. But what about false positives? The loss of misclassifying rainy as sunny hot remains the same as misclassifying sunny as cloudy. So the second term weights differently different types of false positives. It describes the cost of misclassifying the true class C tag as class C. And the same, but in vectorial form, we see that the first term has W matrix, which is diagonal. You are familiar with that as a vector of the class weights that is the input for the weighted cross entropy loss. And the second term, the A matrix, has off-diagonal elements. Each of them is the risk of a different type of false positive, different type of misclassification. So back to our example, if those are the true classes and those are the predictions, we can now have different risk for different misdetection. So for example, if the true class was rain, but we said it's sunny, we can give it a higher risk than the others. So, and note that it doesn't have to be symmetrical, because if we predicted sun and in fact it was rainy, then people will be outside without umbrellas, getting all wet, they will be mad at us. But if we said that it's going to rain, but eventually it was sunny, then everyone's surprised for the best and no harm is done. So it doesn't have to be symmetrical. So the weather categories task is just one example. In many other real-world applications, order matters. Now that we covered the assumptions and limitations of basic categorical classification, we move on to ordinal regression. So basically, throughout this chapter, I will return to the following example. Assume we get an image or measurement of a plant, and we need to estimate its level of stress. Is it experiencing some stress based on, for example, insufficient watering? So we want to know that in order to, for example, adapt irrigation or something like that. So we have categories. We have the no stress category, moderate stress, and complete stress. Basically, that plant is gone. And as in many categories that describe a process through time, we can observe that those are ordered categories. Now let's consider what may happen when ignoring that order and addressing it as a regular categorical classification problem. We may end up with the following confusion matrix. So the y-axis here are the true classes and x are the predictions. So we can see that in the mild cases, the true mild cases in 30% of the time, we predicted those as severe, not even moderate, severe. So this is really far away from the true class. If we are to make a mistake in 30% of the time, so at least let it be with adjacent class. For example, um, instead of mild, say it's moderate. And we can see another such example here. 20% of the severe cases were predicted as no stress. So basically, we want to push those toward the main diagonal. And if we will observe the feature space, that illustration right here, we can see that since we did not provide any constraint regarding the order, then especially in cases where we have lower amounts of data, we may end up with suboptimal cluster relations. So for example, the no stress cluster right here, it came up to be closer to the severe than it is to the moderate. Well, fear not, regression comes to our rescue. So ordinal regression. Let's look at some example where we have ordered categories. So for example, a teenager for age categories is older than a kid. An adult is also older than a kid, but is also older than a teenager, and so on. So we want to really encode that order into our learning process. Ordinal regression in neural networks was introduced in the Anand Rank paper. Basically, the basic concept behind it was to represent the order of the categories through our labels. So instead of using one hot vector where only the true class index is marked in 1 and the rest are zeros, it is suggested in a different approach where for class K, the kth index and everything before it is set to 1 and the rest to 0. So basically, what it does, it encodes distance between those classes. And we can notice that the assumption of classes being mutually exclusive no longer holds. So basically, we cannot use the softmax. We'll use the sigmoid instead. So the labeled vectors now have meaning to the distances between them. Let's revisit the same classification problem. So earlier, we used that as a nominal classification. We got those far away from diagonal values and suboptimal cluster order in the feature space. Let's revisit that. When we use ordinal regression, we now may get that confusion matrix with values being much more closer to the main diagonal. So basically, even if the recall of each class remains the same and the total amount of falses remains the same, the entire risk here is lower because the nature of the mistakes is better. And if we will examine the feature space, we will see that order between those clusters, their nearest neighboring clusters now make more sense. Many architectures designed to solve the ordinal regression for K classes model the problem using K-1 binary classifiers. So as we mentioned before, an adult is older than a kid, but also older than a teen. So each binary classifier divides the world into two possibilities, above or below the category K. So for the plant example, each classifier will output the probability of the condition being greater than a specific stress level. So for example, one binary classifier will model the probability of the stress level of the plant to be above none. Another classifier will have the probability of the stress level to be above mild, and so on and so on. And the reason we only need K-1 classifiers is that if the K-1 classifier have stress level to be above severe, if that probability is above the threshold, that means that we are in the last category, which is the category above severe. It's the Kate category, the complete category. Looking at the following example of output predictions that are above the half threshold, we get the condition that, for example, the stress level to be above moderate past that condition. So it is likely that the stress level is above moderate, but we also got that the probability of the stress to be above mild is lower than threshold. But obviously that does not make sense because those categories are ordered. Everything above moderate is by definition also above mild. So this is a contradiction. This contradiction is called rank inconsistency. Basically, we had no constraints between those binary classifiers. So because what we desire for this monotonous behavior right here. To solve that, the Kroll paper suggests weight train of the output nodes where they only differ in their biases. So basically it enforces the consistency. While it managed to solve the consistency problem, it also introduces a strict limitation, the weight sharing, and that really limits the network capacity. Later on in the Korn paper, they reduced the weight sharing limitation by introducing basically the chain rule and introducing the conditional probability training sets. But in the next chapter of our talk, we will see beyond the available course labels. For this example, let's look on age prediction. Assume that I present you with a picture of this woman and I ask you to estimate an absolute value. What is her exact age? Even though this is not an unfamiliar data domain for us as human annotators, this may still be a difficult task. Now let's assume that for this data set, I have coarse categorical labels. So I provide you with the following prior. This woman belongs to age category 30 to 40. So basically I'm asking you, drop the cursor at this exact location in that segment right here. So this task is still hard because as humans, we make better precise decision when being asked relative question, when we compare alternatives and not being asked to give one absolute answer. And this methodology in decision making is called analytic hierarchy. So the moving window ordinal regression from the last CVPR leverages this concept into the training and inference decision making. So suppose instead of giving you the prior of the course age category, let's say I have age information for a subset. So I present you with two examples that bound that woman age from both sides. So this woman is older than that 31-year-old, and she's also younger than that 38-year-old. Now I ask you, how old is she? You are now able to compare and make a prediction and repeat in an iterative sort-like algorithm way. So far, we talked about discrete categories, while ordered, but yet discrete. But the world is continuous. It's just our mind that is discrete. So we used earlier the example of the plant experiences stages of stress. You can see now that those images were taken from a great time-lapse video created by Adam Chomsky. He filmed that process through 5 days. Okay, so as humans, we tend to categorize in order to just simplify our world. But as a discrete output for a continuous world really serves us optimally. Do we want our machines to mimic our limited labeling capabilities, or we wish they will outperform us? So especially in cases where human expert opinion is required and humans are asked to categorize into finer resolution, in those scenarios, humans tend to lose objectiveness of the categorization task. Finer resolution is really hard to do. and also humans may tend to change their choices when being presented with the same samples again, based on, for example, the order of previous samples that they saw. So in many cases, what we will really have are only coarse labels, coarse categories, but the world is continuous. So some samples do not distinctly belong to just one category, as we saw for the plant stress level. Now say that we have one category for teenagers. Let's say it's up to 18 age, and the second category for young adults starting from 19-year-olds. So an 18-year-old do not distinctly belong to one of those categories more than to the other. So this introduces us a concept from classical clustering, fuzzy class membership, where a sample has partial membership to more than just one class. Now let's consider the scatter of the following clusters. We do not want to force a hard label on the samples that are here between those two clusters. We want to encode membership to more than just one class. For example, using the distance of the samples from each of the cluster centers, as described right here. And the distance, really, it could be Euclidean or it could be exponential distance, and then we'll get a softmax-like form. And we can see that the sum of all class memberships of the sample J sum into 1. And so basically what we'll have here, instead of one hot encoding, we'll get categorical memberships, those soft labels, fuzzy membership to each of those classes. For example, based on the distances, as we said. And Hinton's paper from 2019 described an additional benefits of using soft over integer discrete labels, and that was shown to improve calibration of the network and also to reduce the overconfidence. But what I really love about this approach is that it introduces the relations between our classes by only changing the way we encode the labels. So no special architecture, no k-1 binary classifiers, just plug and play. And the approach we saw earlier still assumes coarse target categories. So we have K categories. However, we can also encode a categorical membership vector into a single real number. So instead of K labels, we get just this one point, a point between the coarse categories. We can do that, for example, by using a weighted average of the categorical membership. So basically, the categorical membership will be the weights, and we multiply them by the, for example, class number. Or if we want that to be between 0 to 1, then we can use uniform steps between 0 to 1 to describe the centers of the clusters. So we get one number. Basically, when we do that, we no longer assume we only have K categories that are important, because we know the world is actually continuous and choosing K is therefore arbitrary. So basically, we're moving from discrete labels distribution into a continuous one. Having real numbers as targets, we may use now linear regression. This will result in clusters being like continuously spread through the axis that connects the cluster centers. That axis describes the order of the classes. The orthogonal axis is then expected to condense. But wait, why should we prefer overlap instead of increasing the margin? Well, that's because in our case, the margin does not really exist. There is no clear cut. So we do not want to force the network to create a margin between an 18-year-old and a 19-year-old while we predict age groups, because it may force it to overfit on irrelevant features. And when we wish to make sure that we generalized well, we want to look on feature space and see that the order of our coarse categories clusters makes sense now. But not only that, we want to, if, for example, we have specific smaller test set where we have finer grained labels, for example, specific ages for this smaller subset, then we want to dive inside each cluster and see inside the cluster the order and see that we generalized well. Check how well we generalized. See that it makes sense. But we will not always have a large number of categories. In some annotation tasks, it will not be feasible to annotate into more than, say, 5 categories. In such cases, when we try to restore labels distribution from those coarse ones, we will get locations where we'll have values like the one right here. Those values do not really exist. In those areas, we face unbalanced regression problem. While unbalanced classification is a subject of great research, unbalanced regression, on the other hand, in deep neural network has room for new progress. In recent CVPR, the balanced MSE was introduced in order to address the imbalance in deep regression. In the last concluding 2 slides, I will summarize the take-home message. So when facing a new task that seems like classification, start from the ground up. Get to know your data. What labels can you expect to have? Coarse categorical? Or can you be provided with a subset of continuous related measurements? Is an expert human opinion required for the training process? And what will be the optimal format and labeling strategy to achieve it? Also, talk to your domain expert. Find out what are the relations between your target classes. What is the cost of each type of misclassification? What other prior assumptions can you make? And on top of that, question the format of the requested output. For example, let's say you are being asked to predict if a student will fail, pass, or excel in an exam. What will benefit the specific business goal better? A discrete answer or a number between 0 to 1. So to summarize, the following diagram can help guide you with your architecture strategy. So we want to ask ourselves, are your target categories ordered? If so, is a continuous output more desirable? Or are some categories less distant from their nearest neighbors than others? In those cases, you may prefer soft labels or linear regression over hard ordinal categorization. I hope this talk was successful in demonstrating the considerations when we are facing what may seem at first glance as straightforward classification, and especially how understanding the relation of your labels may leverage your use of them. Thank you so much. Feel free to reach out via LinkedIn. I will be happy to continue our discussion and get your feedback about the talk. And if you want to read more about the topic, you can find it in my blog. Thank you so much.
No, thank you, Topaz. Yeah, we just have Jeremy asking about if your slides are available and suggestions on where to learn more.
Yeah, well, my slides are not yet available, but you can find more information in my blog post about it.